Okay. Thank you, Mike, for the invitation to come and speak today and the introduction. So I'm going to jump right in. I am willing, as we go along, to answer questions if they come up. I'm going to cover a fair amount of material, so I'll keep it moving, but I would encourage you, if you do have questions, to put them up on the screen, and I'll try and address them as we go along. Okay, let me just start by, I'm going to put these acknowledgements up front. We've had funding support to do work on short-rotation woody crops, in particular willow, from a whole bunch of different organizations over the last number of years, and it's not happening, of course, without that essential support, so we are grateful for that. And I should just acknowledge also that there's a whole host of people that work on this project collectively, both at ESF and both at other academic partners and industrial partners now. So this is certainly not stuff that I do on my own, and it's not going to move forward without these and expanded collaboration, so it's important to acknowledge. What I'm going to do today is just to give a little context, talk about energy use in the United States and where woody biomass fits into our overall energy consumption. And then I'm going to give a short introduction to short-rotation woody crops, a little bit of information on this recent billion-ton 2 update. So the update to what was called the billion-ton study is just released a couple of weeks ago. And then I'm going to key in on willow biomass crops as an example of a short-rotation woody crop for here in the Northeast region, and talk about production, a little bit of environmental benefits, and then the economics of the system, and looking at ways that we might improve the overall economics of the system so that it becomes more viable and deployable across the landscape. So first of all, I just think it's important for us to realize where we are in terms of our energy consumption here in the United States. So this graph shows you what our total energy consumption, or the portions of our total energy consumption here in this pie chart, heavily dependent on fossil fuels. As you can see, about 85% of that energy comes from fossil fuels, and then about 8% of it now is from renewable energy. If you then look at this stacked bar graph and you see the different sources of renewable energy, so hydro is the largest. The second largest source of renewable energy is actually wood. Biofuels and the expansion of biofuels is now third. So collectively, if you think about biofuels and wood being biomass, it's the largest source of renewable energy here in the United States. And then you see the others: wind, waste, geothermal, and solar PV as well. So wood has been, for a long time, an essential part of our renewable energy mix, and will continue to be going forward. So wood comes from a variety of sources. It can come from forest biomass or residues from manufacturing, or from short-rotation woody crops. And so, as Mike mentioned, the focus today is to talk about short-rotation woody crops and an example of the production system that's being developed in the Northeast. One of the advantages of woody biomass is you do have these multiple sources, and so those supplies are often available at different times of the year. And in order to develop projects, especially larger projects, people often want to look at mixed sources so that you have consistent, reliable supply over the year. There are handling and transportation systems in place, for example, for wood coming out of the forest. We've been doing that for years in different industries. And so those systems are there, although talking about the scale of expansion that is being discussed here in the United States, they would have to be expanded considerably in order to be effective to support the need. Okay, so both short-rotation woody crops and forests are low input systems, and so that becomes important, and I'll mention that a little later on when we talk about energy balances and some of the environmental benefits. Okay, so let's just look at this on a scale here of sources of woody biomass. So over here at the left end of this chart, we can talk about natural forest systems or managed forest systems, and then plantation systems. And as you move from the left to the right, you have more intensive management generally of these systems. So here's where short-rotation woody crops fits in, not quite over as far as ecosystems or agriculture systems, but certainly on a forestry sort of scale of perspective, short-rotation woody crops are much more intensive than either plantation or natural forest systems. Okay, so Just examples of short rotation woody crop systems that are being developed. So southern pine is now being looked at as a short rotation woody crop, so sort of to the right side of the plantation forest. Eucalyptus in the southern part of the United States is also now being explored and developed as a short rotation woody crop. Hybrid poplar is being looked at and has been in the pulp and paper industry for a number of years, sort of on 8 to 12-year rotations, but people are now going back and looking at managing that on 2 to 4-year rotations, which is where willow fits in. So more intensive but shorter time cycles closer to an agricultural system is where shrub willow fits in on this scale of perspective. Okay, so the billion-ton update. So this is a long time coming, and this was just released, the billion-ton 2 report. And it's different from billion-ton 1 because it's got county-by-county inventory data that you can actually access online and make use of. It also incorporated economics, which the first study really didn't, and it looks at farm gate price and how much is available using farm gate price as a factor. And it's got a more rigorous treatment of sustainability issues related to resource availability. So just a couple of things to show you out of that. Here is the current sort of yields that are being looked at. These, when I talk about the baseline scenario in another graph or two from this study, these are the sort of yields. So from 3.5 to 6 dry tons per acre per year for these different short rotation woody crops across the United States. Okay, so what did the billion-ton 2 study tell us in terms of millions of dry tons? So in this graph, you had millions of dry tons. You have 3 timelines in each of these scenarios. So how much would be produced in 2017, 2022, and then in 2030. And then you have 3 cost scenarios at $40 a dry ton, at $50 a dry ton, and at $60 a dry ton. So I think one of the things that's important, also then you have 3 different sources of energy crops: perennial grasses in blue, woody crops in red, and annual energy crops in yellow or gold. One of the things I think that's important to note here is that on the $40 a dry ton scenario, so these are numbers for the entire United States, that there isn't much biomass going to be produced from energy crops. So that's something I think is becoming clearer, is that these things cost some money to produce, and that's going to be necessary to produce the quantities that we want. You can see then at $50 and $60 a dry ton, if we just go to the $60 dry ton scenario, you can see that over time we're getting more and more biomass. And in this case, perennial grasses are the predominant source that's coming online. So by 2030, we're talking 255 million dry tons. And perennial grasses, 126 million dry tons from woody crops. So what does that look like in terms of acres, in terms of the production that we're looking at in terms of millions of acres? Again, this graph is set up the same way as the previous one, so we'll just slide down here to the $60 dry ton. That's a number I'm going to use for some analysis later on, so we'll focus on that at this point. And you can see the numbers of acres. So as you scale up to 2030, 43 million tons, 43 million acres for perennial energy crops, and about 18 or 19 million acres for short rotation woody crops. So when you think about the time frame between now and 2030 to be putting in those sort of acreages, it's a sizable effort that's going to be required in order to make that happen. One of the other things that's important from this analysis that needs to be thought of is that these are farm gate prices. I mentioned that before, and there are some important differences in the supply chain once you go from the farm gate and beyond in terms of perennial grasses and woody biomass. Woody biomass can be stored on the stump. It's easier to handle and requires less cost in terms of storage. And so they also ran an analysis where they took the baseline number, which is the one I just showed you for the production of millions of dry tons, and then they adjusted it for $5 a dry ton extra cost for perennial grasses because of the past the farm gate costs, and then $10 a dry ton. And you can see when those extra dollars are added to manage the system to the rest of the biomass to the rest of the supply chain, it makes some differences in terms of what they project is going to happen. So even at $5 a dry ton differential, there'll be more woody biomass and a little less perennial grasses being grown under this projection and the scenario they have. So the thing here that's important to think about is that while they've made significant improvements in this study, it is on gate price, and the rest of the supply chain needs to be thought through, and there's a lot of effort now being done to develop that part of the system for both perennial grasses, crop residues, as well as rotation woody crops. Okay, so that's a snapshot of the billion ton 2 study and numbers and where things are coming out. So overall, the numbers for all perennial energy crops are considerably higher than they were in the first study. And then that they are going to be a significant part of the biomass supply going forward. What I want to do now is shift focus and sort of drill down to a short rotation woody crop here for the Northeast United States. So to talk about willow as an example of a short rotation woody crop that's been under development for about 25 years or so here in the Northeast. There's a large amount of diversity of willow across the world. So there is over 350 species of willow in the world. The focus is really here on shrub willows that are being developed as opposed to tree willows, so not the black willow or weeping willow that a lot of people are familiar with. These are more shrub willows you find along stream banks and those kind of environments. But there are about 175 species of shrub willow around the world. So large genetic variability, and there's a lot of work going on, both in terms of genetics and developing and understanding the genetics and then potentially modifying them, as well as some just traditional breeding. So Larry Smart at Cornell is one of the lead people working on that at this point in time. Willow is a pioneer species, and so it's got some benefits because it is adapted to harsh conditions and marginal conditions, and so that's important when we start looking at the types of land that we can make use of to grow willow. Another advantage of willow is that it coppices well. So after harvesting, it will sprout back, and I'll show you that in a minute in terms of how the cycle is developed and being managed. It grows rapidly, and so you have high biomass production, rapid growth, and canopy closure, and that's important, not only because you need the biomass production, but also because the weed control is important with that canopy closure. So the biomass production potential, we have measured yields as high as 27 oven dry tons per hectare per year. It's around 12 dry tons per acre per year. Those were fertilized and irrigated unimproved clones. And so reaching those on a large scale production level is not necessarily going to occur on a regular basis, but the potential is there to improve on the yields that we have, and I'll talk about that in a little more detail later. Willows established easily from unrooted cuttings, so you just need pieces of stem and you put them in the ground, they root below ground and grow above ground. There are not a lot currently of insect and pest problems, but again, this is something that folks at Cornell are monitoring closely, because if we're going to scale up to millions of acres of short rotation woody crops, we're certainly going to have some insect and pest problems. So we need to be monitoring and be aware of approaches to manage that as it goes forward. We're working here on building off of experience in other places in the world. So there are about 40,000 acres of commercial plantings of willow in Europe currently, largely in Sweden and the UK and some in Germany now. There are about 1,000 acres of willow planted in the US with trials in a bunch of different states and locations. And so this map just gives you an idea of the range of locations where trials of willow, of this shrub willow, have been conducted or are currently being conducted. So across much of the Northeast and out into the Midwest and off into some of the prairie regions of Canada as well. Okay, so what is the biomass production cycle that we're talking about that is currently being recommended? And here's a sort of schematic that shows you. Again, we start with site preparation here on marginal land. We could have lots of discussions about this. It's essential that this is done properly in order to get the crop established. And if you don't get the crop established properly at the beginning, you have lots of challenges. And I'll show you that when we talk about economics, why that's absolutely essential that that occurs properly. You don't want to do it twice. Once you do the site preparation, then you have a planting process where you put the cuttings in the ground. They start growing. This illustrates the sort of double row system that we use here. So 2 rows closer together with gaps on either side. This is really to allow harvesting, so a harvest can straddle one double row and come in and harvest. After the first year, we typically coppice it or cut it down, work with Willow's ability to resprout naturally, and it will resprout, as we see here in this next picture, with a lot more stems in each plant. So this helps develop the rapid canopy closure and helps with the weed control. 1-year-old plants after coppicing look something like this, and then up at the top we have 3-year-old after coppice plants. So they would be on a 4-year root system, but 3 years old above ground. Typically at this point, although we're also looking at going to a 4-year rotation, but then it's time to harvest. So this is typically occurring in the dormant season, and then after harvesting you come back down here to a resprout condition. So we'll resprout the following spring, and you would cycle around again for another 3 or 4 years. If we run on a 3-year cycle, and that's what I'll talk about in terms of economics and environmental parameters going forward, we are currently modeling 7 3-year harvest cycles. So a single planting and 7 3-year cycles is what we're looking at for the management of this crop at this point in time. There's lots of parts of this system that need to be refined and worked on. I'll touch on some of those in a few minutes as we go through the rest of the presentation. So here's planting equipment. This is specialized equipment that's been brought over from Europe. This plant at the top is called the step planter. There's actually now a company that holds a license here in upstate New York to manufacture these here in the United States. And you can see the 1-year-old pieces of stem that are fed into this machine. It then cuts off a section that's 7 or 8 inches long and pushes it down into the ground. This planter does the same sort of thing with 1-year-old stems. The one at the bottom is called an egg bell planter. It does a similar thing with a slightly different process. So those machines are here and available for commercial scale planting. The other issue early on that was a challenge as we looked to try and expand this from research to commercial production is where is the planting stock coming from. So we've been very fortunate to be able to partner with AA Willow out in western New York. And they now have more than 100 acres of willow nursery beds of different varieties that have been selected from the program here at ESF and are now available for scale up to anybody in the US or Canada who's interested in acquiring them, both for biomass production and then for other applications as well. So some of that issue in terms of commercialization of the planting stock and availability is overcome. So just some pictures here to look at the system again. So this is willow that's probably 6 or 7 weeks old. Again, we can see this double row system, 2 rows closer together, and then a wider 5-foot gap over on the side. So we grow it for a year and coppice it. You would then come back in the spring. This is this picture from late May. Again, you can see the double row system here that we have that we are using with the harvesting system that we have. This is what that same field would look like in late June. So if you've done your site preparation well, you will now begin to get canopy closure in the 2nd year. Here's what it looks like by late August. The different colors in that picture from August represent different clones of varieties that are planted across the field, which is an important part of management in terms of minimizing risks going forward. And there's some examples, some shots of 3-year-old willow biomass crops on the left in the dormant season, so it's ready for harvest, and on the right inside near the end of the 3rd dormant. The harvesting system was another barrier going forward. How do you get this material effectively harvested off the field and into a form that can be used readily by end users? New Holland has been working now in collaboration with us and some other people for several years to develop a system based on their forage harvesters. So what you see in this picture is a standard New Holland forage harvester is the prime mover in the back. And the front piece, this header is a specially designed header that they have developed to cut and chop willow. They've also tried it and are working to adapt it for poplar, eucalyptus as well. So in these latest trials, and we have some DOE support that is ongoing to develop and optimize this system, but we're harvesting material that's up to about 5 inches in diameter with this system. It cuts it and chips it into a very nice uniform product, and so that's important because end users were concerned early on with the inconsistency of the product, but this forage chopper produces a very nice consistent end product. Okay, just some examples of collection systems. We've really been looking at trying to make use of equipment that's on the landscape that's not being used during the dormant season. So here's a bunch of pictures using forage wagons, self-unloading forage wagons, and then on the bottom right you can see we would drop that material into just a silage blower or forage blower and load them into trucks either over the top or in the back. Another system that we looked at is using dump wagons, and so as these pictures illustrate, we can go into a dump wagon that'll lift directly into trucks, or we can use these dump wagons and create storage piles near the side of the field that then can be used and supplied to end users at a later point in time. Okay, so just a few comments. That's sort of the production system in a snapshot, and I just want to make a few comments about environmental benefits and then talk about the economics and how we can improve the system overall. So where are we at in terms of a greenhouse gas balance with this system? We did a life cycle analysis that was published in 2003. And this life cycle analysis, the boundaries of the system are illustrated at the bottom. So it started all the way back at nursery operations where the 1-year-old stems were grown that became planting stock. It covered the 7 3-year rotations that I talked about earlier. And it also included removing or grinding up the stools in the field after those 7 rotations. So all the way from nursery operations through those 7-year rotations through to grinding up the stools so you could be planting something else back. What this analysis showed is that this is a low carbon fuel source. So Willow, when you look at that entire cycle, is 3.7 megagrams of CO2 equivalent per hectare emissions over those 7 rotations. So that's where we stood at that point in time. There were a number of issues that we had to model because of the limited amount of data that was available. And so one of those factors that we had a limited amount of data on was below ground biomass. And so this is some new data that we have just recently finished collecting and are now beginning to summarize for publication. But it makes quite a difference in terms of the carbon balance of the system. So on this graph, what we have is below ground biomass in megagrams per hectare, and the orange line shows you what was estimated for the previous life cycle analysis. And then the blue line above it shows you what we've actually measured when we've gone out and dug up root systems in these willow biomass crops and measured the amount of biomass. So there's a significantly higher amount of biomass below ground than we had previously estimated. And what this does is this then changes the system from being a low carbon fuel source to actually being a system that sequesters carbon. So from emitting 3.7 megagrams of CO2 equivalent per hectare over 22 years to being a system that sequesters about 27 or 28 megagrams CO2 equivalent per hectare over its lifespan. So that's going to be an important point going forward and looking at the balances of the products and different types of energy that are generated from these systems. It also makes it clear that we're at the beginning of really understanding these systems effectively, and there's a lot more work that needs to be done in order to understand the different dynamics that are going on in these systems and in order to better quantify these environmental benefits. Okay, wildlife. There's been some work on wildlife and biodiversity benefits. If you plant different stages of willow at different ages or different years, so you get different ages across the landscape as illustrated in this diagram, is probably the way to maximize the benefit in terms of some biodiversity. There's also some things that can be done in terms of landscape placement and selection of the varieties that we will use. There were some folks at Cornell University that spent a number of years looking at bird diversity in willow plantings. And what they found here in this summary graph is that the species diversity in short rotation woody crops, primarily they were looking at willow, so that the bird diversity is very similar to old fields in upstate New York, and not that much different from deciduous forests in the region as well. So there is the potential for a fair amount of biodiversity to be supported in these systems, and as we understand this more going forward, we'll be able to design and manage these systems to optimize that if that's a goal that people build into their management plan. Okay, so the next section I want to talk about is what is the economics of the system, and using the economics as a framework to talk about ways that we need to continue to work to improve the system to make it more affordable and attractive to landowners so that it would be deployed across the landscape. So this picture is just a snapshot of the opening page of a cash flow model that we've developed. It's available on our website to download, and people can change and modify all the parameters in it to suit their local conditions, and then run it. Give an idea of what it would, what the sort of returns would be for fertilization root crops in their region. As I just mentioned, you can change the input parameters throughout this model. That's the way it's designed. The intention was that it would be flexible and widely applicable to a wide range of regions and conditions. It includes all the components of willow biomass crop production, starting the site preparation all the way through the delivery of the biomass to an end user. And so I've listed there a few of the parameters that are included, but there are a lot more that are in there as well. In terms of the numbers that I'm going to show you in the next few slides, we're looking and use the 25-mile delivery distance. Again, this 3-year cycle, 7 rotations is the model, what I have for numbers for this model. We assume a $30 green ton price, or about $60 a dry ton. So referring back to that billion ton study numbers that I showed you, it's at the top end of those ranges of values that were modeled. Okay, so when we run the model as a, in this base case scenario, what does it look like? This is cash flow year by year. So starting in the first year with some site preparation, in year 0, starting in some site preparation and then planting. And as you can see, there's a significant cost in terms of dollars per acre that we have here on the y-axis in terms of getting the crop established. So that is a challenge and a barrier moving forward because that's a significant amount of cash up front to get the crop established. So then you have this 1, 2, 3 years. This first year of growth, then we coppice, so then we have 1, 2, 3 years of growth, and in the 3rd year, during the dormant season, we will harvest. Another 3-year cycle, harvest again. So the black bars are the years that we're harvesting and getting positive cash flow. Overall, when you run this analysis and look at the internal rate of return, it's a little over 5%. So if we take that year by year cash flow and look at it in a cumulative cash flow in terms of, again, dollars per acre, you can see what this pattern looks like. Again, you have this large upfront investment to get the crop established. Here's your first harvest around after 3 years after that first coppicing, and then you have the subsequent harvest over time. And you can see that we're not back to a break-even point under this base case scenario until the 4th harvest, and then you have positive cash flow beyond that. So again, this is a barrier to people, especially in the agricultural community, that are used to dealing with positive, hopefully positive annual cash flows. But this cash flow scenario is a little more challenging because of the upfront costs and the time it takes to recover those costs. But that's what it is for a base case scenario at this point in time. And so what let's look at some factors that we can deal with to adjust that. So Mike asked, the delivered price, Mike, is $60 an oven dry time in this base case scenario. Let me just comment on this previous graph. We also, in this model, have these scenarios where the blue line is what happens if we could increase revenues by 10% and reduce expenditures by 10%. So we call that our optimistic scenario, and then below that, the red line is the pessimistic scenario. So if revenues decrease by 10% and expenditures increase by 10% on that red line, we would not quite break even over the life of the project. So one way to start this is to look at the breakdown of costs, and you can see that the big costs here have to do with harvesting and establishment. So those are two things I mentioned before, that we're working on this harvesting cost and working with Chasing Home to develop a system not only to produce a usable and consistent end product, but something that will drive that cost down. I'll comment about establishment costs, and then this fertilizer cost is something I'll also make a comment on, because I think we're getting to the point to recommend that we do away with fertilizer in this system. We don't seem to get any benefit out of it over time. So the big cost in establishment has to do with cutting costs, because if we're putting in about 6,000 cuttings, these pieces of stem are called cuttings per acre, and we're somewhere in here between 12 and 15 cents per cutting that goes in the ground. You can see that that is a substantial amount of money, and the majority of the establishment cost is associated with that. So working with our nursery partners, figuring out ways to drive that cost lower, where they can still make a profit, but as you decrease your cost, then the internal rate of return will increase significantly. So that is an area that deserves some attention and should be worked on. Okay, so I'm just looking at this comment. I'll talk about energy balances, the question about where that fits into the energy balance diesel fuel factors in a couple of minutes. Okay, I talked about fertilizer. So here's some results. This is biomass in tons, dry tons, metric tons per hectare. And the thing really to focus on here is the third year. So at the end of the 3-year rotation, there's no significant difference between these treatments, these fertilizer treatments. And these fertilizer treatments are, this is a control. We have 2 levels of commercial fertilizer, nitrogen applied as urea, 2 levels of biosolid compost, and 2 levels of digested dairy manure. So we did these trials with 2 clones across 3 sites and have done a series of other trials and find no response to fertilizer application. So if we remove that, as you remember from the previous slide, it's about 10% of the cost, and so that's a significant cost saving going forward. And if we see no benefit in terms of production of the system or overall health of the system, then that would be a wise thing. Here's some work that we're looking at in terms of the effect of the speed of the harvesting system. So this graph shows you harvester speed along the x-axis in miles per hour and harvesting costs. The red line is on 3-year rotation. So when we started the process, we were probably somewhere around 1.5 miles per hour. We think by the end of the project that we're currently working on, it will be somewhere between 3 and 3.5 miles per hour. So significant improvements to be made, and as you can see, because harvesting is a big factor in the overall cost structure, that we can drive those costs down. Another thing to look at is the change from a 3 to 4-year rotation, and so you get some real gains in terms of reduction of harvesting costs on a $ per ton basis when you go to a 4-year rotation, because the harvester is moving more tons of material per acre as it goes across the field. Okay, let's look at yield as a factor for these systems. I'll make some comments about, there's a question about pellets, and I'll make some comments about that in a few minutes. and that doesn't mean that we can address it then. So, not surprisingly, as is the case for all of these energy crops, as you increase yield, your internal rate of return goes up considerably. So, a 50% increase in yield would improve more than double your internal rate of return. So, the work that's being done around this is essential to make these systems viable and successful. Where we at on that, let me just show you a little bit of data that we have based on some trials, a network of 2 long-term trials that have been in the ground now for 4 rotations, and then a network of trials that include new varieties from the breeding program that was started at SUNY in the 1990s. And what we see is, if we just look at this here, we could look at the top clone, but I prefer to look at a mixture of maybe 3 or in some of the cases maybe 5 clones. If we look at the top 3 clones, from old plant material, so material that was just collected from various locations or from the University of Toronto, those are the sort of yields we were getting in the first rotation. If we then look at the 9 trials that we had that include new varieties that came from our breeding program, there's a significant improvement in yield, around 20 or 25%, just from bringing the breeding material, the newly bred and selected material online. The next thing that's important is that we now are consistently seeing an increase in yield from the first rotation to the second and subsequent rotations. And so I had mentioned that in the previous slide and maybe skipped over it too quickly. But when you go from first to second rotation, you typically get about a 20% increase in yield. And then in the longer term trials we have shown that between first and fourth rotation, you can be getting up to a 30% increase in yield. The thinking is that most of that is related to the fact that in the first rotation, the plant is building both a below ground root system and above ground biomass. But in the subsequent rotations, because it's a perennial system, it's not having to expand or use the carbon that it's acquiring to build the root system. So in this scenario, in terms of yield, if we now take those projections going forward and apply them over the 7-year rotations, what does that look like? So if we take that 21% yield increase from first to second rotation, and again go with these 3 clones here and look at what does that mean in terms of an average annual yield over time, that means that over 7 rotations, we're really probably looking at a 14 oven dry tons per hectare per year. If we go and use that 30% increase in the 4th rotation, it goes up a little bit as well. But this is important in terms of modeling this system going forward. A lot of data has been based on first-year rotation yields, and we're seeing that benefit of new varieties there. But we also need to be looking at these long-term dynamics of the system to accurately model yield going forward. Incentives, and so this is something that there's lots of discussion and activity around. This is some analysis that we've done looking at the impact of different types of incentives on the internal rate of return and other aspects of short rotation root crops. So we have in here a base case scenario, this blue line, which is very similar to the base case scenario that I have been talking about in terms of the economics. And this graph shows them across different yield scenarios. So again, you can see the benefit of increased yield of that base case scenario. And then we have different combinations of incentives, annual incentive payments, establishment grants. And so this brown line would represent something similar to the BCAP program that is currently being deployed, where you have 75% of the establishment costs covered in an annual payment. And so if we apply that to Willow, this is what the sort of internal rates of return would look like. This pink line shows the inclusion of also the previous VCAP payments that were available for biomass when it was delivered, and so add extra value and benefit in terms of internal rate of return. So incentives can be important and help move the system forward, especially in terms of overcoming some of the upfront establishment costs that are a barrier moving forward. One of the concerns is that when you look at the examples of short rotation root crops in other places, Sweden, for example, they over-incentivized early in the 1990s, and when those incentives went away, the system crashed very dramatically. And they also had a lot of problems early on with very poor establishment. So they have a lot of these fields that are out there and are not producing in terms of the yield up to the potential that was intended because people didn't establish them effectively in terms of weed control, proper management, predict control. Okay, in terms of markets, where is this material going? As I mentioned earlier, it's most likely to be mixed with other sources of wood biomass for any number of these applications, CHP, co-firing in coal plants, gasification, thermal applications, which I think in the Northeast is something that is going to get more and more attention in the near term, and then biorefinery types of applications. So, if we think about this in terms of the price for biomass, right, people usually want to drive the price here to the left, make it lower. But if we think of adding more value to a ton of biomass, then maybe there's the opportunity to actually provide growers a higher price for the biomass because there's more value added going on at the back end. So if we increase the price, not surprisingly, the delivered price here, and here's the base case at 60, if we increase the price, you have a dramatic change in the internal rate of returns. So let me just talk about one example of how that could occur. There's lots of people working on these biorefinery systems. This is an example of one that we've been working on for wood. Here's the typical process. You grow the wood, you chip it up, and then you use it to produce electricity or heat and power collectively. There's a lot of valuable compounds in any source of biomass. Sugars in terms of hemicellulose and cellulose, lignin if you can get at it and make use of it, plus some smaller quantities of other compounds that are available as well. The process that we have been working on here at ESF just uses water. So you put the chips in a pressurized vessel with water and you cook it for a couple hours at a set temperature. And what happens is the hemicellulose comes out. You also get acetic acid and some furfural and some other products that come out. These sugars can then be used to make any number of other products, ethanol, biobutanol, biodegradable plastics, or used as a base chemical for other products. The part that's left over here can still be used for renewable heat and power in different types of forms. So here we're getting now multiple products out of a ton of biomass going forward. And we really talk about this and look at this process as being this idea of incremental deconstruction. So take the wood apart and pull out the higher value products and get the value out of them and use the rest of it for lower value products like electricity. So in the sort of models that we've been looking at with this system, you can pay for most of the cost of the biomass with the products, with the value of these products, the sugars, the hemicellulose, the acetic acid, and furfural, and other minor products that come out of the system, pretty much cover the cost of the biomass delivered to the facility. I'm going to skip this. This is just a more complicated breakdown of that system, and this really summarizes the comment I just made in terms of the benefit. Let me just show you some pictures here and wrap up. So this is an extraction vessel that we've been working with that holds about 500 pounds of wood chips at a run. And so we load it up and do the hot water extraction in that vessel. This is the extract that comes out of that process. When you're done, this is what the chips look like. These are actually hardwood chips, but we've also done it with willow as well. And so you get this discoloration. Again, here's the extract solution with the sugars and other products in it. That is then run through a filtration system to recover those products. One of the things that's important is some of the other benefits that occur when you cook these chips. So there's this discoloration that occurs, but we've also looked at them in terms of what is their value in terms of making pellets, because you now have a higher lignin content as a proportion because you've removed some of the hemicellulose. And the other thing that's important is the ash content drops considerably. So whereas willow, with its bark on, would not make a premium grade pellet, when you do this hot water extraction process, the ash content actually drops enough that you can then make pellets that make a premium product. There's also this interesting effect that occurs when you remove hemicellulose out of wood. So here is a pellet that is made from wood that after it's been through that hot water extraction process, and here's a pellet, just a normal hardwood pellet. And you can see that over time, putting these in water, you get this breakdown of hardwood pellets, so that's not a usable product, whereas the pellets that are made from this hot water extracted product maintain the consistency over time. So, I'm ready to stop here and deal with questions. This is really just a summary of the main things that we've talked about. Again, these systems are fairly young, and there's a fair amount of work that needs to be done to make them deployable. A number of aspects of the economics that need to occur to make it more effective from that point of view. There's also, and I didn't talk about this so much, the opportunity for getting multiple benefits out of the shortation weed crop system. So I did talk a little bit about biodiversity, but there's also work going on at incorporating these into the landscape to address water quality problems, nutrient runoff from agricultural systems, and those kind of benefits. Also using them to remediate old industrial waste sites. And then again, combining them with other woody biomass feedstocks and increasing the value of each ton of biomass. So I'm done at this point and can go back and address questions if I didn't address the ones that were done earlier. So let me go back to this. I guess I didn't address this energy balance when I talked about greenhouse gases. So the energy balance for Willow, if we take that life cycle analysis that I showed you earlier, and we look at the energy balance from the beginning of the crop through to the edge of the field, for 1 unit of fossil fuel energy that is put into the system, you get 55 usable units of energy stored in wood chips at the edge of the field. If you take the nitrogen fertilizer out of that system, as I talked about earlier, then that energy balance increases to about 1/8. I'll just keep going down the list here, Mike, unless you want to do something differently.
Yeah, no, go ahead. I think you can read them yourself. That's probably the easiest, and yeah, and we'll go from there.
Okay, so this comment about pellets, I think I addressed. So as a raw product, Willow is going to make an industrial grade pellet because of its bulk content. If you want a premium grade pellet, there's other ways to do it, but this hot water extraction process is one way to do this. Ron's question about minimal planting area. So larger is better. 10 acres, I would say, is a minimum that you need to have. Your harvesting costs are going to be higher. If you need to truck that harvester in just to cut 10 acres, which it will do in a few hours, and those 10 acres need to bear the full cost of moving the harvester at some distance on the back of the truck, then the costs are going to be higher for harvesting. The overall cost for biomass will be higher. If you've got a series of fields, 10, 20 acre fields that are within range of 10 or 20 miles that that harvester can just drive to, then it's a more feasible operation. There's comment about slope limitations. Yep, so it's really the limitation, if you're going to use this forage harvester system, is based on what the forage harvester can handle, so sort of an 8 to 10% slope is what the operator is telling me they're dealing with. Melissa has a question about the composition of the extracted solution. So it is primarily hemicellulose sugars in a water solution first. There's also some acetic acid that has some considerable value, a little bit of furfural and other products. And really that solution is then taken and run through a series of off-the-shelf membrane filters to separate out those products.
Are you okay? Are we?
Yeah, I am. I'm just reading the next comment about the chemical wood industry. So there was an extensive chemical wood industry here. Right, so if we have lots of natural gas resources, that's certainly going to be a point of competition with biomass. getting the sugars out of the biomass in these sorts of wood-based biorefineries then allows us to be going to biofuels as well. So the comparison of the economics of these systems, I think, is something that still needs to be worked on, and we really haven't got commercial wood-based biorefineries up and running at this point in time. So I mean, it's a valid question in terms of what the overall economics of the system will be and whether they're viable. The next question about invasiveness of these plants. So if there are types of shrub willow that root sucker, for example, that then increases their potential to spread fairly easily. We eliminate all those very early on in our breeding and selection program. So as we collect material and have collected material across the Northeast and the Midwest, anything that root suckers gets removed from our program. We have not found in all the work that we've done over the years willow successfully reproducing from seed in any of these fields. It's a very short-lived seed and does not do well unless it's under ideal conditions. And most of the egg fields we are in are not ideal by any means. But you would need a sort of riparian sandy bank that is wet with no other competition. So we don't see a big problem in terms of invasiveness. There are deer browse impacts, so this goes back to the size of the field question. If you have too small a field and it's surrounded by hedgerows or forests on three sides, you can end up with a serious deer browse problem if you have deer in your area. If you plant larger fields, it's not as big an issue.
Yeah, there's a bunch of credit emails, so Melissa is the next question.
Okay, thanks. So that's a good question. I'm not sure if you can collect, capturing the salicin or salicylic acid out of that. If you, there's lots of people working on that. If you do some searches in literature databases, there are a lot of people in the medical field that are looking at extracts of willow. Most of it's going to tell you what the extract is because it's proprietary. So I presume that there would be some way that people are working on to do that, and since they just want that high-value product, they probably don't care about the rest of the biomass. So it would be an interesting thing to look at. It's not something we've looked at specifically. So the next question about high yields in the Northeast. So part of that is we have not done as much testing of material in other parts of the country. And then part of it is going to be a moisture availability and consistency of rainfall over the growing season issue, I think. So that's, as you go further out into the Midwest, may become part of the challenge. Certainly the trials we've done, for example, out in Alberta in the prairies, had some limitations on rainfall that lowered yields. As you go further south, so the trials we've tried down in the Carolinas, for example, for the plant material we have, that's probably too warm an environment for them to optimize their growth. And so you need to be looking at different selections of material for those kinds of
Tom Richard on CO2.
Right. So we are currently looking at what happens to the carbon that's stored below ground at the end of the 7 cycles. So we are currently have a trial that is now in its second year where we harvested the willow, killed it, and then ground it up in place, and are monitoring both soil respiration coming off of those fields and the below ground carbon and changes over time. So, Tom, that's something I'll have to tell you about in the near future. I can tell you that in the first year monitoring, the soil respiration rates in the fields where we took off the willow, killed it, and ground it up, were not dramatically different than the soil respiration rates that were occurring in actively growing willow fields beside it. So that's a prize to look at. We look at most of the overall balance.
Is everyone hearing him? It's coming in and out for me a little bit. I don't know if that's common or I'm having the same problem, but There's nothing we can probably do about that. I apologize. Go ahead, Tim.
Melissa asked about rooting hormone. So you don't need any rooting hormone to get willow established. It roots very effectively when you just put a cutting in. So the willow that's being used here, there is a question about the willows that are being used. All the willow that's being used on a wide scale here in North America is based on material from North America. The willow that's been developed in breeding programs in Sweden and the UK, we've brought that material over and tested it here, but it is susceptible to several pests, one in particular, potato leaf poplar, that makes it not a good choice of plant material to use in this part of the world. So we're using material that the breeding program, for example, draws on material that was collected from natural systems across the Northeast and Midwest. So the 7-cycle limit on the willow system that I talked about is not so much a biological limitation, but what happens over time. So this picture at the bottom, this is second rotation willow, the picture that's on the screen now. But what happens over time is when willow resprouts, it tends to have more sprouts on the outer edges of the stool, and over time this 5-foot gap is going to get smaller and smaller to the point that you're not going to be able to get a harvest in. And when you puncture one of these tires and it costs you $1,500 per cycle, that will ruin your economics. So it's really a space and functionality of the system as opposed to a biological limitation in this 7-cycle limit. So in terms of the cost, I would agree that so these costs vary in terms of prices for wood chips. The wood chip market actually in New York State for energy production, they are currently paying between $20 and $25 a green ton in getting the material that they need to the facilities here. So I think there's variations in these costs in different regions. But it's certainly going to be a factor, and if you have long haul distances, that's certainly going to become an issue in terms of the overall economics of the system. So again, the numbers I showed you were based on a 25-mile haul distance. You can take that model and adjust the haul distance and look at the impact that it has on the overall economics, and it is an important factor that needs to be considered when you put these plantations in the ground in terms of where they are relative to the